6.2 Part 2, Differential Equations, Growth and Decay. Most banks pay interest that compounds annually, semi-annually, quarterly, or etc., even daily. The equation that they use to calculate the amount of money you're going to have after a time t at an interest rate r, compounded n times per year, is A equals P times 1 plus r over n to the nt power. And you've seen that before. But have you worked with interest that compounds continuously? I think some of you said you have. The rate of change of the amount of money is proportional to the amount of money when you invest it in an account that pays continuously compounding interest. So that rate of change of the amount of money, again, is the dy dt is proportional to the amount of money, if y is your amount of money. So if we separate the variables and integrate that, we end up with that same equation we had before, c e to the kt. But in this case, we're using the letter P for principal. It's the principal amount of money that you've invested, the initial amount. And instead of k, we're using r for our interest rate. So it's the same equation, but we've changed the variables to make it more user-friendly so that p and r are obvious in this example. So PERT is like SECT, but specific to interest that's compounding continuously. So for example, if you invest $3,000 in an account that compounds interest continuously, how long will it take you to double your money? So we want to double our money. So the amount that we want to end up with is $6,000. The initial investment, the principal, was $3,000. And we probably need our interest rate. Sorry, interest rate equals 1.2%. So we'll fill in the interest rate. And since the rate is written as a fraction, we want to change it to a decimal. So we're going to use 0.012 for r, and then times t. So we divide by 3,000 on both sides. So really that 3,000 was not important for this example because we could double our money. If this is the initial amount that we invest, and 2 would be the doubling of that. So either way, we're going to take the natural log of both sides so that we can solve for t. So natural log of 2 equals 0.012 t, and then divide both sides by 0.012. And t equals whatever natural log of 2 divided by 0.012 is. Which is about 57.76 years. So about 58 years. Newton's law of cooling. You may have learned about it in your science classes, maybe not. It works for anything that's just sitting around cooling. It states that the rate of change of the temperature of an object is proportional to the difference between the object's temperature and its surrounding temperature. So this right here, derivative of y with respect to t, that's the rate of change part. Sorry about that. And k is the proportional, here's is, and then the difference between the temperature, the object of the temperature, or the temperature of the object and its surrounding temperature. So y will be the temperature of the object and t is the surrounding temperature. So just like we've done before, if we take this equation here and we multiply both sides by t, get the y on the left side and the t's on the right side, so separate your variables and integrate, you will end up with this cooling model here. Y equals the temperature, surrounding temperature, plus the original temperature of the object minus the surrounding temperature, and y will be the temperature of the object currently, times e to the kt, and k is some proportionality constant, and t is time. So this Newton's law of cooling always reduces to this cooling model, which we can use to find the temperature of any object So let's pretend we're forensic scientists. We show up at a crime scene and we find the dead body, and it's in a room with a constant temperature of 60 degrees. We take the temperature of the dead body, and it's currently 85 degrees. We know that the temperature of the body should be 98.6 if it's alive, so it's been cooling for a while. 10 minutes later, we take another temperature of the body, and it's 80 degrees. So how long has this person been dead? Because the time of death is very important in a crime investigation. So we're going to use the cooling model derived from Newton's law of cooling. Y equals T plus the original temperature of the object minus T times e to the KT. So the first thing we're going to do is fill in the current temperature of the body is 85. The temperature of the surrounding area is 60. The original temperature of the object we have to assume is 98.6 approximately. And the surrounding temperature is 60 times e to the k times t. So we've got two variables still. We don't know the time, and we don't know the proportionality constant. So we know that we took the temperature 10 minutes later, and we can use that information also. Let's solve this a little bit. So we'll subtract 60, just kind of condense it. So 25 equals 98.6 minus 60 is 38.6. And then dividing both sides by 38.6. We get approximately 0.64766 for e to the kt. Right? We also know that we took the temperature 10 minutes later, and the temperature of the body was 80. The surrounding temp is still a constant 60. The original temp was 98.6. But T is no longer just time, it's time plus 10 more minutes. So if we subtract 60 here, we get 20 equals 38.6 times e to the, let's distribute that k in there, kt plus 10k. Dividing both sides by 38.6, we get e. Well, okay, remember what to do with this e with an exponent that's added. You can break it up as e to the kt times e to the 10k. And then over here, 20 divided by 38.6 is about 0.5183813. And if we divide, well, let's leave it like that. So we know that here, e to the kt is 0.64766. Let's put that in here. Because we have two variables, we needed two equations to continue working. So here's our new equation. And we can divide both sides by 0.64766. So e to the 10k is approximately equal to 0.8. Taking the natural log of both sides, we have the natural log of 0.8 equals 10k. And divide both sides by 10. K will be approximately negative 0.02231. So now that we know K, we can go back and find T. So we're going to take that K, and we can plug it back in to here to find T. So we'll have e to the negative 0.02231 equals 0.64766. So we can take the natural log of both sides. Oh, then the e will be gone. So that will just be negative 0.02231 t. divide both sides by negative 0.02231. So T is approximately 19.5, and the units on that will be minutes. So it was about 20 minutes, 19 and a half minutes after the crime was committed that we showed up at the crime scene. So that's just a cool application of Newton's law of cooling and other growth and decay models. This would be a decay model using calculus. The homework is page 421, 43 to 61 up, 65, 71, and 73.